How long is the side of this green rectangle? 12 centimetres. What if we write it 12.0 centimetres? Is there any difference? The answer is yes. It's an important difference, particularly if you are an engineer and you're building something that needs to fit very precisely together. Otherwise you could end up with gaps. First of all, what was the difference? 12 centimetres could be any number that rounds to 12 centimetres. So that could be 11.5 all the way up to 12.5. 12.5 you could round up to 13 or down to 12. Usually you round up, but anywhere within that range is what 12 centimetres represents. 12.0 centimetres represents anything from 11.95 up to 12.05. So you can see there's quite a bit of difference between these ranges. This top one, the range is 1.0. The range is the final minus the initial, or the difference between two, so 12.5 minus 11.5. Whereas the bottom, the range is only 0.1. So 12.05 minus 11.95. So you imagine if you had two pieces of wood carefully measured out to cover a 10 metre length, and these pieces of wood are measured to be 5 metres each. Each of those pieces of wood, if they're measured on a metre scale, could both be rounded up from 4.5 metres. So that could potentially leave us 1 metre short if we haven't measured these 5 metre lengths to the right number of, or to the right precision. We'll just leave it there at the moment. Now, the way that we talk about these things is by using something called significant figures or decimal places. The key of what we're after here is precision. Precision, very important. That's why I've put an exclamation mark and underlining it. So let's go back to 12, since that's the number we have up there. We've got 12. 12 is measured to two significant figures, two SF significant figures. 12.0 is measured to three significant figures, 3 SF. And we would also say that this is to one decimal place, 1 dp. So significant figures and decimal places are both measurements or annotations, if you like, of the accuracy of a measurement. Most of the time it's pretty obvious. In the case of 12.0 here, you can see that there's accuracy to that level. And even the 12, you can see there's accuracy to that level. But if you have something like 200, without someone stating what the precision is for a number like 200, you don't know whether that's to 1, 2 or 3 SF. Okay, because you've only got that hundreds figure of the 2. But this might be very precisely measured to 200. It might not be rounded up from 170 or down from 247. So this could actually be very precisely measured, in which case we need to have the little statement beside it saying 3SF. So that's really important that we understand these ideas. When it comes to calculations, it can be a little bit tricky. I'm just going to give you the two rules, or two of the rules, and then if there's time I'll do an example. So the rules for calculations let's just write rules for calculations. Two main rules. We're going to underline this with a nice wiggly line, because wiggly lines are easier to make look tidy, and it's hard to be tidy at the best of times here. And rule number one, if you're multiplying or dividing, you should use significant figures, figs. So it means if you've got an area measurement and you've got 5 meters by 2 meters, if your measurements are to the nearest centimetre, that would be 5.00 metres and 2.00 metres. I should write this down. We may as well do this as a full example. Let's move that over here. Here's our example. 5.00 metres times by 2.00 metres. So this could be a square that we're measuring and we're trying to find the area. So 5 times 2 is 10, and because if we were giving an unrounded value, it would be 10.000, however many zeros you feel like putting in from your calculator. A calculator automatically goes to the least number of significant figures that a number will have, so it won't give these extra decimal places at the end. But your final answer needs to be rounded using the significant figures to the least number of significant figures from the original data. So 5.00 is 3 significant figures, 2.00 is 3 significant figures, so 3 significant figures for our final answer is 10.0 metres. Okay, and if for some reason one of these measurements was only to 2 significant figures, 5.0, then we would have to default our answer also to 2 significant figures. So we would get rid of that and it would just be 10, and then we'll go to 2SF. Because this 2 significant figure reading is a limitation on our final result. We can't be certain that our final answer can be given to a greater precision, because that smaller, it's like the weakest link in a chain. Okay, so going back over here to our multiplying and dividing, we've also got adding and subtracting. And what are we doing by adding and subtracting? Well, in this case, we can just use the decimal places. So if you're adding or subtracting, use decimal places. And we'll be giving an example of that as well. So if we have again the 2 length measurements and we're sticking them together, one of them is 1.5 and the other one is 2.13, and they're both meters. Okay, so this time they're different, and we're just adding the lengths to each other. So to find the total length, we're going to go 1.5 plus 2.13, and putting it in this way you can actually see where the problem arises. We're missing an important figure there, so our limiting factor is this 1.5, because 1.5 could be 1.45 up to 1.55. And the 2.13 could be 2.125 up to 2.135. So it's kind of pointless having this extra 3 figure. That's why that gets dropped off with rounding. But we have to perform the calculation using our unrounded values first. And then our final answer would be, let's move that out of the way. Our final answer is going to be rounded to the least number of decimal places, which is 2, or the first to the tens in this case. So 3.6 meters. And once again, that's just because it's pointless giving accuracy to that second decimal place, because one of our values up the top only goes to one decimal place and could potentially include a range that is much wider than that extra bit of information. So we don't need that bit of information, and we would be lying to our engineer if we gave him this value rather than this value, because the top value we can't be confident that it's precise to there. It could be all the way up even to 3.68, all the way down to 3.58. So it's a better value, it's more representative to say this, unless, I guess technically speaking, you could give them the full calculation so they can see it and make up their own mind just what they're going to do. Okay. Very quickly, just looking back up again at the area measurement, and the reason why we use the least number of significant figures is if you imagine this small strip is the range of error for the width. That is the possible range of error that it could be. If you're limited in one way, say if this is the 2 significant figure reading, and you've just got a very thin strip of error in the other direction, so that's 3SF, you can see which one's going to be the limiting factor, can't you? The 2 significant figure one is much more significant when it comes down to the final area. So that's the one that's going to have the big effect. So the 2 significant figure, that's why we would use the 2SF in multiplying and dividing. Okay, hopefully that's helped you. If you'd like more examples, please feel free to email me. physicslounge@gmail.com. Here's the whole thing. You probably can't see it all there, but let's just go and have a look. So we started off over there. We looked at what the range of values could be for different statements of precision. That's how I came up with the idea of significant figures and decimal places. We've looked at some rules for calculating, multiplying and dividing using significant figures. Use the least number of significant figures in your final answer. That's what that's getting at. And for adding or subtracting, use decimal places. That is, use the least number of decimal places for your final answer. So there we go, longish video. Well done for listening all the way. Send your comments and questions. Thank you.